Hello friends, welcome to CEC Live Lectures. Dear friends, today in this session we are going to continue further in our series on natural products and spectroscopy. Since our previous two lectures we are talking on carbohydrates, and as there is a lot more content left for you, so we are going to talk more on carbohydrates today also. Friends, for the discussion on the topic we have with us in our studios Dr. Vandana. Dr. Vandana is an assistant professor and she is teaching in Department of Chemistry, Dal Singh College, University of Delhi. Dr. Vandana has the immense enthusiasm as well as immense experience, which always helps us out in understanding various topics of chemistry. Friends, if you wish to ask questions from Dr. Vandana on today's topic, then do call us through our toll-free number. Our number is 1800110430. I repeat, our number is 1800110430. You are just requested to call in the last 10 minutes of the lecture. Now I would like to welcome our guest, Dr. Vandana, once again.
Hello. Thank you so much, ma'am. Hello viewers, we were taking a series natural product and spectroscopy, and in this series we have started a new topic, that is carbohydrates. In last two lectures we have discussed about the introductory part of the carbohydrate, that is what are carbohydrates, and we were discussing three definitions of carbohydrate, which one of which was the hydrates of carbon. Then we were not satisfied with this definition, we were taking another definition of carbohydrates. How can we define completely carbohydrate? That was, these are the compounds which are polyhydroxy aldehydes or ketones, or in other words we can say these are the polymers of these compounds, that is polyhydroxy aldehydes or ketones, or the compounds which yields these compounds on hydrolysis. Then still we were noticing a technique, that was mutarotation, in which we were observed about the alpha D glucopyranose structure and beta D glucopyranose structure, which were because of mutarotation, because of interchangeable these two forms via open chain structure. So we were not satisfied that definition also, that was polyhydroxy aldehydes or ketones, or the compounds which were yields these on hydrolysis. So actual definition for carbohydrates was the hemiacetal. The cyclic structure explains all the characteristic properties of the carbohydrates. And thereafter we were discussing about the glucose. We were discussing in detail about the chemical properties, how can we elucidate, how can we deduce the glucose structure, in which we have discussed three parts. Open chain structure of glucose, that thereafter we were discussing about the cyclic structure as well as the configuration part of the glucose. We have discussed about the very specific technique, that is mutarotation, and we were discussing about the reducing sugars, we were discussing about non-reducing sugars. In today's lecture we will continue carbohydrates, that will includes the structure elucidation of fructose, that is polyhydroxy keto sugar. We will discuss about the glycosidic structure of glucose, pyranose structure and furanose structure of fructose, and we will discuss many things in today's lecture, that is disaccharides, sucrose or maltose, and thereafter we will discuss about the polysaccharides also. Let us begin with the structure of fructose. Ketohexoses means hexoses, carbohydrates which contains ketonic group. All the ketohexoses that occur in nature have the keto group adjacent to a terminal CH2OH group. Thus, there are three chiral carbon atoms present in the structural formula of a ketohexose. You were very much aware of this fact, that what is a chiral carbon atom? A carbon atom which has four atoms or groups different. For example, D minus, and what is this minus indicate? That this indicates that LIVO, and this is indicates D, that is this hydroxyl group lies on right hand side. So D and L fructose, D and L sorbose, D tagatose, L cyclose. Out of these only D fructose, L sorbose and D tagatose occur in nature. And you can see these are the structures of different ketohexoses. It is D-fructose. You can see the structure of D-fructose. These are three chiral carbon atom, 1, 2 and 3, as the four atoms attached to these particular carbon atoms are different in nature. This is the L-sorbose, this is D-tagatose, you can see this is the L-cyclose. So these are the examples of ketohexoses. Now, how can we deduce, how can we elucidate, or how can we establish the structure of fructose? D-fructose is present in the free state in some fruits, honey, and in combined form with the glucose in the most important disaccharide sucrose. Fructose is also quite sweet. Naturally occurring fructose is levorotatory. As you can see, this sign, it shows levorotatory and is therefore called as, also known as levulose. The open chain structure of D-fructose is derived on the basis of the following observations, as we have discussed in case of glucose also. For the molecular formula, we need to take the elemental analysis, that is, how can we elucidate the molecular formula for which we have to take the elemental analysis. This is carbon, hydrogen, oxygen, and the molecular weight determination. It concluded the molecular formula for fructose C6H12O6. Fructose forms the oxime when treated with hydroxylamine, and a cyanohydrin is formed with the hydrogen cyanide. This reaction indicates the presence of carbonyl group. If you have read about the carbonyl group, these are the characteristic properties of the carbonyl compound that when reacts with oxime, they will made hydroxylamine, and while treated with cyanohydrin, they will made hydrogen cyanide. So these reactions are observed for fructose. So we can say fructose contains a carbonyl group. A fructose is a reducing sugar which contains a hemiacetal structure. It reduces Tollens reagent. This is an oxidizing agent, and a Fehling solution, another oxidizing agent. So we can say it is a reducing sugar, because in the last lecture we have discussed in details what sugars are reducing in nature and what sugars are non-reducing in nature. We have discussed that reducing sugars have hemiacetal structure, so they can reduce Tollens reagent, or we can say simply oxidizing agent. Fructose is reduced with sodium amalgam and water to a mixture of hexahydric alcohols, sorbitol and mannitol. The alcohols on treatment with hydroiodic acid and red phosphorus at 100 degrees Celsius gives a mixture of N-hexane and 2-iodohexane. So this is the another reaction given by fructose. Fructose forms the pentaacetate when treated with acetic anhydride and anhydrous sodium acetate, indicating the presence of 5 hydroxyl groups. So fructose is not oxidized by bromine water, right? Oxidation with nitric acid, however, gives a mixture of trihydroxyglutaric acid, tartaric acid and glycolic acid. And all these acid contain fewer number of carbon atom than the fructose molecule. The carbonyl group in the fructose must be present as a keto group. These are the reactions given by fructose. You can see when reacting, as we can see this reaction, acetic anhydride and sodium acetate will give pentaacetate. It means there are 5 hydroxyl group in fructose, right? When we see this reaction, that is with phenylhydrazine, it will give phenylhydrazone. So it contains either a ketonic group or aldehydic group. With HCN, it gives cyanohydrin. With NH2OH, hydroxylamine, it will give oxime. With HCN followed by hydrolysis, it will gives you 2-methylhexanoic acid, or you can say hydroxy acid, which on reaction with hydrogen iodide or phosphorus, or we can say on reduction, will give you 2-methylhexanoic acid. So there are 6 carbon atoms in a chain. Another reaction we can see over here is that oxidation, strong oxidation are giving these 3 compounds, right? And on reduction with sodium and alcohol, it is giving hexahydric alcohol, which on further reduction with hydrogen iodide and phosphorus will give you N-hexane and 2-iodohexane. Another reactions we can say with Tollens reagent, it gives a positive test. With Fehling solution, it gives a positive test. With bromine water, it will not react with bromine water. So collectively, all these reactions come to concluded that fructose is a molecule which contains 5 hydroxyl group and a ketonic group also, and there are 6 carbon atoms in a chain, as these reactions gives you. This is hexanoic acid, means 6 carbon in a chain, and this is N-hexane, means 6 carbon in a straight chain. So all these reactions can calculate this kind of a structure for fructose. Here we are not describing about the chirality of the carbon. Here we are simply saying that fructose is simply a 6 carbon atom in a straight chain, and there is a ketonic group at carbon number 2. Now configuration of D-fructose, that whether it is we can say D plus or D minus. We have already seen that D-fructose gives the same osazone as obtained from D-glucose. This means that the configuration at C3, C4 and C5 is same in the 2 sugars. We are talking about glucose, we are comparing fructose with glucose. So configuration about C3, C4 and C5, we are talking about absolute configuration is the same within 2 sugars, that is D-glucose and D-fructose. Thus the configuration of D-fructose is established. We have already concluded the ketonic part, so it can only be the structure of D-fructose. You can see D-glucose, D-fructose both are giving the same type of osazone by reacting with phenylhydrazine, 3 molecules of phenylhydrazine. We have discussed in detail how glucose and fructose react with phenylhydrazine and how many phenylhydrazine consumption in this particular reaction. Now the third part of the D-fructose, this is cyclic structure. The following observation cannot be explained by open chain structure of D-fructose. Fructose does not form a bisulfite addition product. Fructose undergo mutarotation in aqueous solution. For example, it has a specific rotation from minus 133 degree changes to minus 92 degree. So it is not at all a specific value, but it is changes from this value to this value. As in case of glucose, fructose also gives 2 methyl glycosides. We were discussing in detail in the last lecture, known as methyl fructoside when treated with methyl alcohol in the presence of HCl. To explain above fact, a cyclic hemiketal structure for fructose has been proposed. We get 2 forms of this cyclic structure with the generation of anomeric carbon. You know what is anomeric carbon? In this structure, this carbon is anomeric in nature. If you see the position of this hydroxyl group with respect to all the atoms attached to the carbon, it is alpha D fructopyranose, as it is resembled with pyran structure, and this is with the position of this hydroxyl group. All rest of the atoms are same except this OH and CH2O. This is beta D fructopyranose. So we can have 2 structures for the fructose designated as alpha and beta fructopyranose, and these are the, we can say, Haworth structure. In the crystalline form, fructose probably exists in the pyranose form with the beta isomer predominating. Alpha form has not been isolated in this case. In case of fructose I am talking about. However, fructose always occurs in furanose form when combined in natural product. And you can see these are the structures in a furanose form. This is beta D fructofuranose, this is alpha D fructofuranose. And when we compare these structure, you can see this chart shows the different melting points as well as the specific rotation of the corresponding compounds. These are beta D fructopyranose pentacetate, this is alpha D fructopyranose pentacetate, and this is methyl alpha D, beta D fructopyranose, and you can see the difference in melting point as well as the specific rotation. Conversions. How can you convert one sugar to another sugar? You can say, first of all, we are taking the conversion of an aldose to ketose, that is a sugar containing aldehydic group can be converted to a sugar which contains a keto group. For example, we are taking here the example of conversion of D-glucose to D-fructose. How can we convert? You can see these are the number of reagents taking part in this particular reaction. This is the structure of glucose. You can see this is the aldehyde group at the terminal carbon, and when we react with phenylhydrazine, you can see this particular osazone is formed when we are taking reaction with this phenylhydrazine. 3 molecules are consumption over here. And after hydrolysis, acidic hydrolysis, you can see this is the protonated water molecule, and on heating you will get a ozone. This is nothing but a you can see the structure of ozone. On reduction with zinc in acidic medium, that is in acetic acid, you will get the D-fructose. So this is how we can convert D-glucose into D-fructose. Another conversion is here, conversion of a ketose. This is D-fructose into the corresponding aldose. Corresponding aldose means the carbon number is same. In the aldehydic molecule product, we can say aldose. You can see this is the D-fructose, first of all, where we are doing the reduction with nickel, and you will get two isomers. You can see this is the possibility with this hydroxyl group on right hand side. This is the another possibility, hydroxyl group on. So these are the enantiomers, we can say simply. You know what are enantiomers? Enantiomers are the mirror images of each other, we can say non-superimposable mirror images of each other. Thereafter, we are doing the strong oxidation with the HNO3, concentrated HNO3. You can see the terminal, this is CH2OH, get changes to a carboxylic group. Here both the groups can changes easily, carboxylic, so only one molecule, that is CH2OH, hydroxyl group, get changes to carboxylic acid. On heating, both the isomers yields lactone. You can see this kind of lactone present over here, and after subsequent reduction with sodium and mercury, you will get the corresponding aldose. This is the glucose, D-glucose, you can say. So this is how we can convert a ketose. From ketonic group we can convert to aldehydic group. Now conversion of an aldose to its epimer. The aldose is oxidized with bromine water to give the corresponding aldonic acid. We have discussed in earlier slides, which on treatment with pyridine gives a mixture of the original acid and its epimeric atomic acid. These acids are converted into corresponding lactone, that is cyclic ketone, separated and reduced with sodium amalgam to give the original aldose and its C2 epimer. You know what are epimers? Which are having the different configuration at carbon number 2. Thus, D-glucose may be converted into D-mannose. If we are talking about D-glucose, the relation of D-glucose and D-mannose, they are epimers. That is, we can see this is the, if you see the carefully the structure of D-glucose and D-mannose. If we see this carbon atom, particularly this carbon atom in glucose and this carbon atom in mannose, rest of the structure in D-glucose and D-mannose is same apart from this carbon. So these are epimers. We can say what kind of isomers they are. When they are different in one chiral carbon atom, they are at carbon number 2, they are epimers. How can we convert one epimer to another epimer? You can see over here, this is D-glucose. First of all, we are doing the oxidation with bromine water. This aldehydic group get converted to carboxylic acid. Then we are doing reacting with pyridine, and so we can have the another epimeric of this D-gluconic converted to D-mannonic acid. On heating, it gives a first of all lactone. This is a cyclic ketone, and on reduction with sodium and mercury, you will get D-mannose. So this is how you can convert one epimer to another epimer. The rough degradation. Degradation, as you can see, if we decrease a series of carbon by one carbon, if we shorten the chain, the rough degradation is used to shorten the chain by a similar unit. The rough degradation involves oxidation of aldose to an aldonic acid using bromine water. Oxidative decarboxylation of this aldonic acid degraded it to next lower aldose using hydrogen peroxide and ferric sulfate. We will see in coming slides what we are talking about. D-ribose can be degraded to D-erythrose as follows. If you can see, this is the structure of D-ribose, D minus, this is the levo compound D-ribose, and you if you remember, this particular D is related to this related configuration of hydroxyl group. When we are doing oxidation with bromine water, this aldehyde get converted to carboxylic group. On further reacting with ferrous sulfate in hydrogen peroxide, it will changes to D-erythrose. Right. So you can see one chiral carbon atom is degraded over here. Another degradation, Wool degradation. This is the reverse of Kiliani-Fisher synthesis. In the last lecture, we were discussing about detail how can we upgrade these series. This is how we can, this was Kiliani-Fisher synthesis, and Wool degradation is just reverse of this particular synthesis or upgradation for sugars. The aldose is, this is the example of D-glucose can convert it to D-arabinose via different kind of steps. The aldose is converted to its oxime first. You can see with the hydroxylamine it is get converted to oxime. This is the oxime which undergoes simultaneous acetylation. You can see how acetylation took place. This is acetic anhydride in presence of sodium acetate. Thereafter and dehydration to the penta-O-acetyl nitrile, and dehydration took place in presence of zinc chloride when treated with acetic anhydride in the presence of anhydrous sodium acetate. We were talking about that. Loss of HCN, you get this kind of product. You can see this oxime get converted to this cyano, and all these hydroxyl group get acetylated by acetic anhydride. Loss of HCN together with deacetylation occurs when the nitrile is treated with ammonical silver oxide. You can see this is silver oxide in presence of ammonia. So, we can say ammonical silver oxide to give the lower sugar. First of all, we get this kind of product, and at the last you will get D-arabinose, that is one carbon get reduced in this particular sugar. Another degradation is here, Wehrmann degradation. This degradation of amide of sugar acid by a variation of Hofmann reaction. So, here what includes Hofmann reaction? If you remember, we were discussing in details while discussing about the reaction of amide, what is the Hofmann degradation of amides. On treatment with HCl or bromide, amide undergoes Hofmann degradation to the intermediate isocyanate, which then disproportionates to the lower aldose. You can see this is what? This is calcium gluconate obtained from glucose, and when reacting with HCl hydrogen chloride, it will give you a lactone. This is from glucose, so this is called D-gluconolactone, and when it reacts with ammonia and ethanol, it will give you a amide. This is D-gluconamide, and sodium hypochlorite will give you isocyanate. You can see this is isocyanate, N double bond C double bond O, and subsequent rearrangement from here you can see how it took place. Hofmann bromamide degradation, you will get D-arabinose when reacting with sodium hydroxide. Now, very important part comes in discussion, that is determination of the ring size. How can we determine the ring size of glucose and fructose? Here we are talking about the pyranose structure of the glucose, and which were proved by many methods including X-ray analysis and periodate oxidations. How it took place? We can see evidence for, first of all, we are discussing about the pyranose structure of D plus glucose. This method was developed by Haworth and Hurst. These were the scientists in 1927. D-glucose is refluxed with methanol in the presence of a small amount of HCl first of all to produce methyl glucoside. How can we produce? You can see this is the particular reaction. This is the D plus glucopyranose. If you see this curved or waved line with hydroxyl group, we can say it can be alpha form, it can be beta form. So, when it is reacting with methanol in HCl, we will get the glucopyranoside, methyl glucopyranoside. The methyl glucoside so obtained is methylated. So, all the hydroxyl group now methylated with the excess of dimethyl sulfate in the presence of sodium hydroxide to give what? All the hydroxyl group get methylated and will give you methyl tetra O methyl D-glucoside. This on hydrolysis with dilute HCl gives tetra O methyl D-glucose. Here we can say this is the dimethyl sulfate, this in presence of NOH. You can see all the hydroxyl group get methylated. So, we can say what is this? This is methyl 2,3,4,6 tetra O methyl D plus glucopyranoside. When reacting with HCl, this methoxy group get converted to hydroxyl group. right, and it will yield 2,3,4,6 tetra O methyl D plus glucopyranoside. When it is reacted with bromine at 90 degrees Celsius, you will get a lactone. This is what? Lactone, and it is named as 2,3,4,6 tetra O methyl D gluconolactone, which on strong oxidation with HNO3 will give you trimethoxyglutaric acid. So now we will discuss what these reactions are, give indications. How can these particular reaction gives indication that what should be the size of the ring, of the pyranose ring. Tetra-O-methyl glucose on oxidation with bromine gives lactone. We have discussed the lactone on further oxidation with HNO3 affords trimethoxyglutaric acid. Now, following assumption can be made. One carboxylic group of this acid comes from lactone, and this is the lactonic, and it gives you one carboxylic acid. The second carboxylic acid is derived from the non-methylated carbon. You can say this is non-methylated carbon, right, and from CHOH that is involved in the ring formation of the sugar. So there are three methoxy groups. What are these? 1, 2 and 3. We are talking about these three methoxy group, right. So there are three methoxy group in the lactone ring, and the C5 hydroxyl must be involved in the ring formation. Therefore, the lactone is what? 2,3,4,6 tetra O methyl gluconolactone. So we can say on the basis of above reaction and assumption, D-glucose must have the structure D-glucopyranose, and it can apply to both anomeric isomers, that is alpha and beta isomers. So hope you understood the ring. How can we assumption, or how can we determine the ring size of D-glucopyranose? Thank you so much.
With this note, thank you so very much for giving us this session. Friends, you are requested to be with us as we are back after a short break. Thank you.
Thank you.
Hello friends, welcome back to this session. Friends, as you know that today we are talking on carbohydrates, and for the discussion on the topic we have with us in our studios Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry, Dalsin College, University of Delhi. So let's welcome our guest Dr. Vandana, and let's try to have a vicious session once again. And friends, you have liberty to talk to us through our toll-free number. Our number is 1-800-110-430. I repeat, our number is 1-800-110-430. Now I would like to welcome our guest Dr. Vandana once again. Hello ma'am, welcome to the session.
Hello viewers, we were talking about in the lecture of carbohydrates part 3, we were talking about the structure of fructose. We have discussed in detail about the open chain structure, cyclic structure, as well as the configuration part of the D-Fructose, that is a levulose. And thereafter we were discussing about many things. We have discussed a very important part, that was the pyranose structure of D-glucose. How can we determine the structure of pyranose? Then we have discussed about the various techniques, how can we degrade the sugars, and we have discussed Wehrmann degradation, rough degradation. So hope you understood these lectures. If you have any query, you can mail me. My mail ID is ronakvandana@gmail.com. Let us continue this part, and we will discuss in detail the furanose structure of D-glucose also. So let us start it. Fischer in 1914 prepared the methyl glucoside in a different way. He dissolves glucose in methanol and added to that 1% HCl, that is hydrochloric acid. The mixture was allowed to stand at 0 degrees Celsius. He obtained a syrup instead of a crystalline product. This syrup was subsequently shown to be a mixture of alpha and beta glucofuranosides. The end product in this case comes out to be dimethyl tartaric acid. We will see in details the reactions. The formation of dimethyl D-tartaric acid indicates that there are two methoxy group within the ring, that is lactone is gamma lactone. Here you can see this is D-glucofuranose. If you see, this is the furan structure. It resembles with furan structure. And this wavy hydroxyl group shows the alpha or beta form. When we are reacting with methanol in presence of HCl, that is we are forming the glycofuranoside. Thereafter we are reacting with dimethyl sulfate in presence of NaOH. So same here as we have noticed in case of pyranose structure, all the hydroxyl group get acetylated and we are getting the methyl 2,3,5,6 tetra O methyl D-glucofuranoside. And on reaction with HCl, it will give you this particular, this is wrong, it is giving this particular reaction, and this is the product of 2,3,5,6 tetra O methyl D-glucose. Thereafter its structure is given as this, as we have discussed, we have seen. This is with bromine water at 90 degrees Celsius, it will gives you lactone, this particular kind of lactone. And hence glucose has got furanose structure named as glucofuranose. It must be noted here that glucofuranose has not been isolated. The structure is deduced on the basis of isolation of methyl D-glucofuranoside. So here you can see, after a strong oxidizing agent reacting with a strong oxidizing agent, we are getting this dimethyl tartaric acid. So all these particular reactions, you can see tetra O methyl D-glucose. It shows there are there are 4 chiral atoms, so we can determine the ring size in case of furanose also. Now we will discuss in detail about the sucrose. You know what is sucrose? It is a disaccharide, that is a carbohydrate which on hydrolysis will give you 2 unit of monosaccharide. This is nothing, this is a ordinary table sugar, right? And it is a disaccharide of course. Sucrose, the most widely occurring disaccharide, is found in all photosynthetic plants and is obtained commercially from the sugar cane or sugar beets. The structure of sucrose is based on the following evidence. First of all, we are elucidating the molecular formula which comes to be concluded from the elemental weight determination part, and on acid catalyzed hydrolysis 1 mole of sucrose yields 1 mole of D-glucose and 1 mole of D-fructose. So we can say sucrose is made up of 2 monosaccharide which are D-glucose and D-fructose. And this is the structure of fructose, which is a beta furanose because of this hydroxyl position. Sucrose is a non-reducing sugar. It gives negative test with Benedict's and Tollens solution. These are oxidizing agent. Sucrose does not form an oxazone and does not undergo mutarotation. So it does not have alpha or beta form. These facts mean that neither the glucose nor the fructose portion of sucrose has a hemiacetal group, because we have discussed in the last lecture that glucose as well as fructose lies in a mutarotation, that is they have alpha beta forms. But as you can see, it does not form oxazone, it does not go under mutarotation. So glucose, neither glucose nor fructose has a hemiacetal structure in this particular molecule, that is sucrose. Thus the 2 hexoses must have a glycosidic linkage, and that involves C1, that is carbon number 1 of glucose, and carbon number 2 of fructose, for only in this way both carbonyl groups be present as full acetals, and we can say glycosides. So you can see this is the alpha glucosidic linkage, this is the alpha carbon from glucose, and this is the beta fructosidic linkage, and you can see this is the furan structure and this is the paran structure. So overall this is a structure of sucrose, and you can see the carbon number also, carbon number 1, 2, 3, 4, 5, 6. Here you can also calculate this, and we can also represent this particular structure in this way also. You can see this glucose part or glucose unit is in a chair form. The stereochemistry of the glycosidic linkage can be inferred from experiments done with enzymes. How can we say that a particular linkage is alpha or beta? This is very important information you must keep in mind. Sucrose is hydrolyzed by an alpha glucosidase obtained from yeast, but not hydrolyzed by beta glucosidase enzymes. What it shows? It shows this particular hydrolysis shows that alpha configuration at the glucosidic portion. Here we are talking about this alpha because the hydrolysis takes place by alpha enzyme only. Here we are talking about. Now sucrose is also hydrolyzed by sucrose, an enzyme known to hydrolyze beta fructofuranosides, but not alpha fructofuranosides. We are talking about this part, and this hydrolysis indicates a beta configuration at a fructoside portion. So both these points concluded the stereochemistry of glycosidic linkage, which linkage is alpha or which linkage is beta. Methylation of sucrose gives an octamethyl derivative which on hydrolysis gives 2,3,4,6 tetraomethyl D-glucose and 1,3,4,6 tetraomethyl D-fructose. The identities of these two products demonstrate that the glucose portion is a pyranoside and the fructose portion is beta furanoside. The structure of sucrose has been confirmed by X-ray analysis also, and any structure if we want to confirm can be confirmed by synthesis also, as we can do in the analytical analysis also. So we are doing here, we can confirm this particular structure of sucrose by synthesis also. Now another disaccharide is here, that is maltose. When starch, what is a starch? Let me tell you in small portion. Starch is a polysaccharides, and you know what are polysaccharides, which contains more than 100 units or which on hydrolysis will give you the monosaccharides, or we can say disaccharides also, oligosaccharides also. When starch is hydrolyzed by the enzyme diastage, one product is a disaccharide known as maltose. When 1 mole of maltose is subjected to acid catalyzed hydrolysis, it yields 2 mole of glucose. Unlike sucrose, maltose is a reducing sugar. We have discussed recently, that is sucrose is a non-reducing sugar, that it does not reduce the oxidizing agent, Tollens reagent, Benedict's Tollens. But when we are talking about maltose, it is a reducing sugar and it gives positive test with failing Benedict's and Tollens solution. Maltose also reacts with phenylhydrazine to form a monophenyl acetone, that is it involves 2 molecules of phenylhydrazine. You can see maltose exists in 2 anomeric forms. It means it is showing the mutarotation. First of one is alpha plus maltose, and which specific rotation at 25 degrees Celsius is plus 168 degree. As well as another anomeric forms is also here. This is beta plus maltose, which is showing specific rotation at 25 degrees Celsius. This is plus 112. The maltose therefore undergo mutarotation to yield an equilibrium mixture alpha and beta, And open chain structure, as far as we are talking about open chain structure of maltose, it has this specific rotation, that is plus 136 degree. Above facts, all these above facts demonstrate that one of the glucose residues of the maltose present in a hemiacetal form and other therefore must be present as a glucoside form. The configuration of this glucosidic linkage can be inferred as alpha. How we concluded that this particular linkage is alpha, as we have discussed in last slide, because maltose is hydrolyzed by the enzyme, that is alpha enzyme, alpha glucosidase enzyme, and not by beta glucosidase enzyme. So here you can see this is the structure of maltose. There are the two units of monosaccharide, that is, you can see these are exact same, these are nothing but glucose, and here this structure can also represent like this, that is in chair form. And what is this linkage? This is alpha D glucosidic linkage. Maltose reacts with bromine water to form a monocarboxylic acid, maltonic acid. It is also shows that the presence of only one hemiacetal group, right? We can confirm it again. Methylation of maltonic acid followed by hydrolysis gives 2346 tetra O methyl D glucose and 2356 tetra O methyl D gluconic acid. The first product has a free OH at carbon number 5. These are the reaction, we will talk about these also. Let us first read all these. The first product has a free OH as carbon number 5, indicate that non-reducing glucose portion is present as a pyranoside. That the second product 2356 tetra O methyl D gluconic acid has a free OH at C4, indicate that this position was involved in a glycosidic linkage with the non-reducing part of glucose, second glucose. Only the size of the reducing glucose ring needs to be determined. How can we determine this? As we have done earlier also, methylation we can done, methylation of maltose followed by hydrolysis gives 2346 tetra O methyl D glucose and 236 tri O methyl D glucose. The free OH at carbon number 5 in the later product indicates that it must have been involved in the oxide ring and the reducing glucose is present as of pyranose. Let us see how we have discussed. This is the complete reactions. How can we conclude it? But let us see one by one. This is maltose and you can see the two molecules linked together, two glucose molecule linked together through alpha glycosidic linkage. And if we see these two particular reaction, if we react this in bromine water, we can see one glucose is in hemiacetal structure while another does not. You can see if we oxidize this molecule with bromine water, with we can get this kind of maltonic acid. Here you can see this ring can break up over here and you will get this converted to carboxylic group. Now another structure we can prove that what kind of structure for another glucose is here, that is another glucose does not exist in hemiacetal structure. We have discussed, let us see through reaction. If we see, first of all we have to react with methanol, that there we have to convert this particular OH into this methoxy group. Thereafter we have reacted this particular maltose or this particular methoxy group, methoxy compound with dimethyl sulfate in presence of a base, let us say NaOH. You can see all the hydroxyl group in maltose get converted to acetyl, or we can say acetylation happens over here, and we can say these are the methoxy group converted from hydroxyl group. After hydrolysis, that particular compound, we are talking about this methylated product, on hydrolysis it will gives you this particular, these two structures. You can see this methoxy group get converted to OH and it is 236 tri O methyl D glucose, and we can say, we can see, observe, this is a pyranose structure and this is the another structure here. This is the hydroxyl group, this is also hydroxyl group. So only 2,3 trimethoxy, tri O methyl. and this is 2,3,4,6 tetra O methyl D glucose in a pyranose form. Now let us see this maltonic acid. This is what? We are getting this from maltose, that is with mild oxidizing agent. We are not oxidizing all the oxidizable group, but we are oxidizing only a particular group. So we are getting this kind of. Now when we are reacting this particular maltonic acid with dimethyl sulfate in presence of a base, you will get this kind of product. Followed by hydrolysis, you will get 2,3,4,6 tetra O methyl glucose in a pyranose form and 2,3,5,6. So we can say one molecule is in a hemiacetal structure while another molecule does not. So this is how we can determine the structure of maltose. Now this type of structure we can deduce for the maltose. You can see these are the two units of glucose, and this is the beta glucosidic linkage in a pyranose forms. And this is nothing, we can say this is the chair form of maltose, which shows the beta glucosidic linkage over here. Now another disaccharide is here, that is lactose. Lactose is a disaccharide present in the milk of humans, cows and almost all other mammals. Lactose is a reducing sugar that hydrolyzes to give a molecule of glucose and a second molecule of galactose. As far as the glycosidic linkage is concerned, it has beta linkage. How it confirmed, let us see in coming slides. We can see this is a structure of lactose. You can see this is the beta glucosidic linkage, this is a galactose. As far as the linkage is concerned, which type of linkage is here, you can simply react with a particular enzyme. If it is hydrolyzed to the monosaccharide by beta, then it is a beta glucosidic linkage, as we have seen in earlier slide. If it is hydrolyzed by alpha enzyme, then it will be alpha. So simply we can see this is a beta glucosidic linkage, and this part coming from glucose and this part coming from galactose. We can represent same structure in chair form also. Now polysaccharides. Polysaccharides, also known as glycans, consist of monosaccharides joined together by glycosidic linkage, as we have seen in case of disaccharides, lactose, maltose or sucrose. Polysaccharides that are polymers of a single monosaccharide are called homopolysaccharide, and that are polymers of more than one type of monosaccharide are called heteropolysaccharide. Simply, a homopolysaccharide consisting of glucose monomeric unit is called a glucan. One consisting of glucose units is a galactan, and so on. Here you can see a particular polysaccharide, and this is nothing but a alpha 1 to 4 glycosidic linkage. It shows a particular polysaccharide. You can see this N over here. This unit is repeated again and again, and you can say that N, let us say N is more than 500. Three important polysaccharide, all of which are glucans, are starch, means on hydrolysis that will contain glucose, starch, glycogen and cellulose. Starch is the principal food reserve of plants. Glycogen functions as a carbohydrates reserve for animals. Cellulose serves as a structure material in plants. Let us see first polysaccharide, that is starch. Starch occurs as microscopic granules in the roots, tubers and seeds of plants. Corn, potatoes, wheat and rice are important commercial sources of starch. Heating starch with water causes the granules to swell and produce a colloidal suspension from which two major components can be isolated. One fraction is called amylose and the other amylopectin. Most starches yields 10 to 20% amylose and 80 to 90% amylopectin. Physical measurement shows that amylose typically consists of more than 1000 D-glucopyranoside units connecting in a linkage between carbon number 1 of one unit and carbon number 4 of the next unit. Thus, in the ring size of the glucose unit in the configuration of glycosidic linkages, then amylose resembles maltose. Chains of D-glucose units with alpha glycosidic linkages such as those of amylose tend to assume a helical arrangement. This arrangement results in a compact shape for the amylose molecule even though its molecular weight is quite large. You can see this is 1,50,000 to 6 lakh. Amylopectin has a structure similar to that of amylose, that is, it has alpha linkage, glycosidic linkage, carbon number 1 to 4, with the exception that in amylopectin and the chains are branched. Branching takes place between carbon number 6 of one glucose unit and carbon number 1 of another unit, and that occurs at intervals of 20 to 25 glucose units. Physical measurements indicate that amylopectin has a molecular weight of 1 to 6 million. Thus, amylopectin consists of hundreds of interconnecting chains of 20 to 25 glucose units each. So, you have understood in today's lecture, we have discussed in detail about the fructose structure. We have seen that fructose contains a ketonic group at carbon number 2. We have seen the open chain structure of fructose in which we have seen there are 5 hydroxyl groups. Let us have a recap of this lecture. If you see that fructose contains a 5 hydroxyl group. How can we deduce that? Simply by reacting with acetic anhydride. If you see, we have seen that when we can deduce this structure of fructose, when we reacting with acetic anhydride, all the hydroxyl group get converted to acetate group. We can see when reacting with phenyl hydrazine, there is a formation of the hydrazone which were resemble with the glucose, and when reacting with hydrogen cyanide, this was the resemble with the ketonic group. It will gives you cyanohydrin. With hydroxylamine, it will give you oxime. So, it shows there is a ketonic group in the further shows that it has a ketonic group. With SCN followed by acidic hydrolysis, it will gives you 2-methyl hexanoic acid. So, it shows that there is a 6 carbon chain attached in a straight chain way. Further reduction shows that it gives a hexahydric alcohol first of all when reacting with sodium and alcohol, and on further reduction with hydrogen iodide and phosphorus, it gives you N-hexane. These all reactions shows when we were talking about that this can be a fructose structure, but all the chemical properties of fructose cannot be satisfied this structure. Thereafter, we were discussing about the configuration part of the D-fructose with the help of osazone formation, because fructose and glucose gives same kind of osazone. So, we can say that the configuration around carbon number 3, 4 and 5 about chiral carbon atom we are talking about. So, both have the same structure around carbon number 3, 4 and 5. So, this is how we have deduced the structure open chain structure of, or we can say configuration of fructose. Thereafter, we have discussed about the cyclic structure of D-fructose. We were discussing about alpha D and beta D-fructopyranose structure. We have discussed in detail about the conversions also. You can see how we can convert aldose to ketose or ketose to aldose, or we can convert one epimer to another epimer. These were the reactions we were talking about. Then we have discussed about the degradation part. How can we reduce the chain by one carbon atom? We have also discussed how can we upgrade the carbon chain by one carbon atom. We have discussed in detail for that. Kiliani-Fischer synthesis. For degradation part, we have discussed rough degradation. We have discussed about wool degradation. We have discussed Weirman degradation. However, it is not in very much use Weirman degradation. We were preferably use rough degradation for the sucrose. Very important part we have discussed today about the determination of ring size of glucose, and we have discussed about the pyranose structure of glucose. We have discussed about the furanose structure of the glucose. Reactions more or less was same. First of all, we need to react the particular molecule with the methanol in presence of HCl. Then we were reacting these methylated molecule, or we can say pyranoside, glucopyranoside with dimethyl sulfate and NaOH, then reacting with HCl. So, same kind of reaction we were using for the determination of ring size. And we have discussed about the furanose structure of D-glucose also. Then we have discussed 3 disaccharides also, sucrose, second one was maltose, and third one was lactose. Then we have discussed about how can we say that there is a particular kind of linkage between the monosaccharide to form a disaccharide with the help of enzymes. The particular enzymes when we use for the hydrolysis of this disaccharide which is responsible for the particular kind of linkage between the monosaccharides in a disaccharides. Then we have discussed about the polysaccharides in detail. We have discussed the structure of starch. So, hope you understood this carbohydrates. If you have any query, you can mail me, or you can if you have any suggestion, you can also mail me. My mail ID is ronakvandana@gmail.com. Thank you so much.
With this note, thank you, and thank you so very much for giving us this precious session on carbohydrates. Friends, we would like to tell you all that now we have completed with all the lectures in the series Natural Products and Spectroscopy. If you have any query or suggestion or feedback for the entire series, then do write to us at info.cec@nic.in. And yes, of course, if you feel so that there is some topics you would like us to conduct for you, definitely we will conduct for you. You just need to send us the topic. First of all, you can see all the lectures on YouTube, and afterwards, of course, you can write to us. So we are taking your leave today with the promise that we are going to start a new series in near future, where we are going to invite our guest Dr. Vandana once again. So dear friends, be in touch, keep writing to us, and yes, keep watching us.
Thank you so much.
Thank you, ma'am.
Thank you so much.